All right, so what we're going to do is we're going to race these two objects down to the bottom. Obviously, hoop, ball. In terms of formulas, the hoop has a formula of mr squared. The ball, it's a solid ball, is 2/5 mr squared. And I think just holding my hand, this has more mass. Which one do you think will get to the bottom first? Ball, hoop, a tie, or they burst into flames in neither. So let's just do gut feeling. Not going to ask you why you think it. Gut feeling, who says that the hoop is going to make it down first? 2, 3, 4, 5, 6. Who says the ball is going to make it down first? A tie and bursting into flames. Oh, that should be everybody. All right. It would be nice not to have to chase these or to damage anything when that falls off. All right, here we go. Let's use this so it's split fair. Stop. There seems to be a tilt that way. Okay. Here we go. Congratulations. All right, now I have two hoops. mr squared. Which one do you think will make down first? Small hoop, big hoop? And I think the masses are about the same. Small hoop, big hoop, tie. All right, small hoop. 1, 2, 3, 4. Big hoop. 1, 2. Tie. Small hoop slightly, but not a whole lot. It would have been nice if they had used a different metal here so that the thickness was the same. Ideally, it would be a tie. In reality, the small one just edged it out slightly. Why? Anyone's speculation about how to know which one's going to win?
The more mass is like in the middle, the faster it's gonna go because the harder it is to stop.
Oh, you're working just fine, and then at the end you decided to take a left turn. The more mass that's in the middle, what again?
The harder it is to start, the more energy required to
So when you were turning these right here, the one that had more mass in the middle, you said was harder to move than this thing?
No.
So more mass in the middle.
Easier to move.
Yes. So the ball has more mass in the middle than the hoop does. It is easier to get this going than it is to get this moving. this beat this because it's thicker, and so therefore more mass is closer to the center than this one is. If I race the ball and this thicker hoop,
Still the ball.
I would think so. So, when looking at some of these formulas, I got mr squared, 2/5 mr squared, 1/3 ml squared. What is the indication that you have more mass in the middle? If I had a hollow sphere instead of a solid one, a hollow sphere, the formula is 2/3 mr squared. Which has more mass in the middle, the solid or the hollow one? Hollow has more mass in the middle? Is that what I'm hearing?
The solid.
You're saying solid has more mass in the middle. Did you say solid before? And I just missed it? No? Okay. Yeah, hollow, they've taken a chunk out of the middle. So if I had a solid ball and a hollow ball, the solid ball would go faster. But what's the difference between the solid and the hollow in terms of moment of inertia? What's the key difference? So look at, I have this formula and I have that formula. What is the big difference?
The denominator.
The what?
The denominator and
Oh,
the
okay.
2/3 and 2/5.
Or in general, the coefficient, just the total fraction in front. The smaller this fraction is, the more the mass is towards this middle, towards the center axis of rotation. Grace?
Wouldn't it be like the other way around, since 2/3 is like if you were converting to a decimal number, it would be larger than 2/5, because 2/3 is like 0.66 and 2/5 is like 0.4. Would it,
Yep.
like, why are they smaller numbers if the smaller fraction indicates a larger mass?
No, the smaller fraction indicates more of the mass is towards the middle.
Okay,
A greater proportion of the mass is at that axis of rotation.
okay.
So the smaller that fraction is, the easier it is to get going, and the easier it is to stop it. That'll come in handy for one of the master sets. All right, questions to hear? All right, so let's talk about torque. Now, the total torque is equal to I alpha as was written on the board earlier. But how do we actually find an individual torque? If I got 5 torques, I need to figure out how to find each torque before I can figure out what the total is. When torque deals with getting things to rotate, it's as force is an influence that might cause acceleration. Torque is an influence that might cause angular acceleration, to get something to rotate. In order to close the door, I need to apply torque. But if I want to close the door with as little effort as possible, where do I apply force to the door in order to get it to close? We have a simulated door right here. There we go, a simulated door. If I want to close the door, where do I push on it?
In the middle.
In the middle of the door? Or one that still required more, I could still do it with less effort. Seems like that's a lot of wasted energy right there. Most of you have closed doors in your lifetime. I'm willing to bet.
It has to be like to the right and,
To the right.
or I don't know how to,
When you say in the middle, as in middle this way?
the middle of the door,
Middle, so,
like where the door handle is. Like.
oh, okay, that vertically
Yeah.
middle.
Yeah.
Okay, not the other middle. All right. So where's the door handle usually?
The center.
Maybe like a little bit lower.
All right. The door handle's right there. When you say the middle, I'm immediately thinking here.
I meant like vertically.
Okay.
In the middle.
Okay, it's a little bit lower because they assume people are shorter than I am. What about in terms of horizontally? Where's the doorknob or handle?
The left, or, well, it depends on what side of the door you're on, but.
So talk in general.
The opposite end? The opposite side?
Of,
Like the opposite of the door hinge?
yeah, of the hinge. Yeah, you were almost there. All right. Why do you suppose they put the door handle there and not here?
Most people are right-handed.
It would be harder.
I think left-handed that'd be for left-handed people there.
It would be harder, I feel like whenever you try to close the door without the handle, it's a little bit more force than like.
So if I'm opening the door, let's keep it unlocked for right now, and it will just naturally swing open. There we go. If I want to slam the door open, should I push on it right here? Where should I push in order to slam it open? Okay, or a little bit farther on if you can. All right, so where you apply a force does matter. The direction in which you apply a force does matter, because obviously pushing there and pushing there has two completely different results. So, how far you are from the axis, hinges in this case, how far you are from the axis matters, how much force you apply matters, and the direction of the force matters. So this is all summed up in the really nice math equation, R tau equals R cross F. We are dealing with a cross multiplication now. We dealt with dot products. This is a cross product. Dot products give us a scalar, cross products give us a vector. And again, for the purists, an axial vector or a pseudo vector. Now, so this is how far from axis of rotation. Force. And this takes into account relationship between the direction of R and the direction of the force. A little bit more detail. R is it's a vector, obviously, because I got the vector symbol there. A vector from the axis of rotation, which I will abbreviate as AOR, to where the force is applied. So if I have an overhead view of a door, and we are gonna put the hinge right on the very end, like that. If I apply a force here, R, my moment arm, it's called a moment arm, or lever arm. Somewhere I had a marker that was right very nicely. R is a vector from here to here. That's my R. I get the biggest torque if R and F are perpendicular. So when a dot product multiplies vectors that are in the same direction, cross product does vectors that are perpendicular. So we get maximum torque if R, the moment arm, is perpendicular to the force, as in this case. Questions to hear? Grace?
What does torque mean in the context of cars? Like I've heard before, like a car may have this many pounds of torque. What does that mean exactly?
It'd be foot-pounds of torque, probably. You have a shaft that rotates, and it's the influence that's causing that shaft. So the bigger the number, the more more torque, and therefore the more angular acceleration. Therefore, you can generate faster speeds in this thing that's rotating. Not a car guy, so I'm sure there's more detail that a car guy could go into. Actually, for most car guys, an excruciating amount of detail. That's probably down there. All right, so let's just do a quick and dirty problem here. I've got my hinge, I got a door from here to here. I'll apply a force there of 3 newtons. We'll make this 2 meters. What is the torque? Someone go for it.
The Newton's K hat or something.
Oh, I was expecting no direction in the first time someone did it. All right, so first let's talk about you said 3 newtons?
Yeah,
Why 3 newtons?
that's all.
That's the force. I'm looking for a torque.
Isn't torque just force and direction? Or with angular?
All right. Sorry, I missed the last thing you said.
Isn't torque like angular force?
It is like angular force. So we have to take into account not only that 3 newtons, but we also have to take the 2 meters into account.
So it would be 3 over 1 times 2 over, if you're cross multiplying?
No, it's not a cross multiplication. That's different. It would be 3 over 1 times 2 over 1, or just 3 times 2.
Cross product is a vector though, right?
Yeah, we will. So let's just get the magnitude first. What's the magnitude of the torque?
6 newtons.
All right, 6 what?
Newtons.
Are you stopping?
Newtons per meter.
You multiply, how'd you get 6?
2 times 3.
Okay, 2 what?
2 meters times 3 newtons.
Therefore, the units would be,
2 newtons over, or sorry, 6 newtons.
yeah, or Newton meters. Typically said Newton meters instead of meter newtons, but if you wrote down meter newtons, check. Now be careful though. If you write down meter newtons, that's not a meter newton, that's a millinewton. A meter newton has a dot in between it. Or typically written as Newton meters, but again, meter newtons is fine, just don't forget the dot. If there's no dot here, capital N is not a normal prefix, and so you can probably get away with that. All right, now direction. What is the direction of the torque?
Which way is positive?
Which way do you want to make positive?
Whatever way it's going, the problem.
So, we'll make that positive. And J hat, I guess our radial vector is going like that. So, J hat. All right, once you establish 2 of them, the third one is set. K hat now is in a very specific direction. It is a right-handed coordinate system that was traditionally used. So, way you do it, so I cross J is equal to K. I hat cross J hat is equal to K hat. So I hat down, J hat's to the right. So you take your right hand, put your hand in the direction of the first vector, I hat. I got 360 degrees in which I can have my hand, but I want to cross with J hat, so I want my fingers to curl towards J hat. So I hat cross J hat, my thumb points out of the board, so K hat is out of the board.